everyone for joining today. I'm Neil Lawrence. I'm Professor of Machine Learning at the University of Cambridge. Welcome. So this event, an AI Revolution in Science, is the first public event from the Accelerate Program for Scientific Discovery. This program is a new initiative from Cambridge University's Department of Computer Science and Technology, and it's been set up with the ambition of supporting a step change in scientific discovery through the use of machine learning. So machine learning and AI are already being successfully used in many areas of science, and researchers at Cambridge are using machine learning as part of efforts to improve healthcare outcomes, monitor environmental changes, and to develop new materials. Outside the university, impressive advances in the use of machine learning to tackle major scientific questions, such as how do proteins fold, how is climate change affecting the Earth, have also attracted widespread attention. So these high-profile successes can act as beacons, inspiring researchers to pursue ambitious projects at the interface of machine learning and the sciences. But if we're going to achieve the wider ambitions for AI and science, we need to create techniques, collaborations, and resources that put cutting-edge AI tools into the hands of the scientists. Our ambition is the Accelerate program can build these bridges we need to achieve these outcomes. The program is supported by a donation from Schmidt Futures, a philanthropic initiative founded by Eric and Wendy Schmidt. And today we'll be looking at the role that AI could play in advancing the frontiers of science and how researchers can benefit from advances in AI technologies. So to explore these issues, I'm delighted that we've been joined by three speakers working at the forefront of AI for science. And they are Kyle Kremner, Professor of Physics and Data Science at New York University, Emily Schuckborough, Director of Cambridge Zero at the University of Cambridge, and Yolanda Gill, who's Professor of Computer Science at USC. Unfortunately, Pushmi Kohli, who was due to join us, and he is Head of AI for Science at DeepMind, was called away at last minute by a family emergency. So that's all the sort of stuff from me, the boring stuff, and now the exciting stuff from, I'm so pleased to have these three speakers here. They're three of my favorite people doing some extremely inspiring work at the interface of machine learning, AI, and the sciences. And our first speaker is Kyle Kremner, who is Professor of Physics and Data Science and the Executive Director of the Morse Sloan Data Science Environment at New York University. His research sits at the intersection of physics, statistics, and machine learning, and he is a proponent of open science, sustainable software, and community cyber infrastructure. Over to you, Kyle.
Well, thank you very much, Neil, for having me. I'm really looking forward to the discussion we're going to have. It's certainly a very timely topic to be asking about how AI is going to be impacting science and what kind of revolutions we either are experiencing or should expect. So I thought I would start before we get into the AI part by kind of stepping back and just thinking about science broadly. And a good way to do that is to sort of Google for the first image you get for the scientific method. And so here's one of the ones that you find. And so I think it's important at the very beginning just to remind ourselves that that the scientific method is really a process. And in addition to trying to extract information from data, which is where you would expect AI to be effective, there are other aspects of the scientific method, which include developing theories, trying to formulate hypotheses and interesting questions, trying to think about what observations or experiments one might perform to test those hypotheses. And then once you've done that and you actually have collected data, then of course you want to test those theories in detail, and that's one of the most grounded and kind of mathematically precise aspects of the entire process. But it's only one aspect of the entire process. So a lot of what I do is in the physical sciences, and I think a lot about the role of AI and machine learning in the physical sciences. And there I'm thinking about things like particle colliders, neuroscience. You also have things like, not really the physical sciences, but other areas where you have simulations that describe what's going on. And my point here is that when we think about theory in the modern context, it's not just an equation that you write down on your coffee mug, like this one that I have here, but they're often very complicated predictions about what you expect to see. And so these examples that you see about what would you expect an image of a black hole to look like, or how proteins fold, or air around an airplane, they're very, very complicated predictions, but you should think of those simulators as the modern day version of what predictions look like. Now, when you pair that together with new programming languages that are very expressive and and high power computing, you have the ability to generate a lot of synthetic data from these simulators, and those are essentially the predictions. But ironically, the situation that you have doesn't actually work very well with statistical inference. It turns out these types of simulators, while they produce high fidelity simulations of the real data, they're very difficult to invert. And because what we would often want to do, you can think of the simulators as going from the kind of theory to predicting what you would expect the data to look like. But often we want to look at the data and then try to infer something about the theory. And it turns out that as the simulators become more and more complicated, this inverse problem becomes more and more difficult. So when you think about, say, just that aspect of it, and you look at what do scientists, what have we been doing traditionally, typically that type of data analysis has involved, handcrafted types of data analysis that's largely guided and informed by expert knowledge and theoretical insight and the kinds of things that you think about scientists doing. And what's happened recently is the pendulum has swung very much in the other direction. And I would say starting with kind of the big data revolution and continued into the deep learning era, which is to sort of eschew expert features and to instead try to move to some kind of end-to-end learning predictive framing of the problem and to be as data-driven as possible. And data-driven, it sounds good, but it's also kind of an assumption that that's necessarily the right direction to go. And I'd say that the pendulum kind of reached its peak, and you started to see papers, articles like this, like the end of theory, and that the data deluge makes the scientific method obsolete. And also quotes from people like Peter Norvig saying, a riff on this adage that all models are wrong, and increasingly you can succeed without them. And so here you're really seeing a radical departure from the scientific method of where basically just we're going to throw data at it and AI is going to basically completely change how we do things. And while it's exciting and certainly gets your attention, it's not really how I think about it. And I think increasingly the AI community is starting to realize that that is not really the end of the story. So, so what people are starting to realize is that there's so this is Judea Pearl's ladder or his hierarchy of causality. And the lowest rung on this ladder are the kinds of questions you can answer with kind of traditional statistics where you have a lot of data. And so even if you have an infinite amount of data and an infinite amount of computing power, you're kind of stuck to a certain rung in this ladder of kinds of questions that you can address. And this is the sort of seeing rung of the ladder, or sometimes referred to as association. Higher level questions are really important in science, and you can think of as doing. And so, like, what happens if I intervene on a system? How will it respond? And that's of course very important for science, and that's important for just being humans. That's how babies learn about the world. And when we think about AI, we definitely want to be able to reason in this way. And there's another rung in the ladder, which you can think of as kind of imagination, where you're thinking about not just answering what if questions, but like what would happen if I had done something else. So these aren't even really experiments that you can do in principle. They have to imagine you have to imagine these kinds of scenarios. And so these are kind of the highest rung in the ladder of questions. And this is all formalized. It's not just mathematically. And so people realize that if we want to get to AI, we're going to need to be able to hit these kinds of questions. And I think if you go back to looking at the scientific method, you see there's all sorts of what if questions and why questions. And what we're really after in the end is like the mechanism, right? And so with that in mind, and you think about where we are with AI right now, it's very good for some parts of this loop. But right now, AI is not particularly great at generating new hypotheses. It's not particularly great in trying to think about what experiment should I go do next if I want to test those hypotheses. And so that's partially why I'm really interested in this interplay between AI and the physical sciences, where you have simulators, because those simulators don't just generate a bunch of data, they're causal generative models of the data. So you can intervene in the simulators. And I think what would be really interesting is to see, can we get AI algorithms and techniques that can, for instance, recover the ground truth mechanisms that we have encoded in these kinds of simulators, The path to doing that will be super useful for scientists right now, but if we have like a long-term vision, I think that this is kind of a necessary step. And so we see now a lot, the pendulum has kind of swung back, and there's a lot of emphasis on these sort of hybrid approaches where you're trying to figure out how to leverage domain knowledge, and while maybe sometimes just allowing kind of black box style machine learning to do what it's good at if we don't understand what's going on. And there's a really interesting area of trying to align the architectures of machine learning algorithms with the actual mechanisms that you would expect in some sort of, physical model. And I think that's like just a very interesting direction. And so I'll end just with this kind of these bullet points, which are that the starting point is that we have these simulators that already have mechanistic models in them, but the way that they interact leads to these very difficult inverse problems. And machine learning is definitely helping there right now. And what's interesting is that if it looks like in the next few years, we might get to a point where machine learning can really just do this. And if it can, it will allow us to basically bridge microscopic phenomena to some kind of larger scale emergent phenomena and serve as some kind of effective model between them. And that would be a really important step if we can do that in a semi-automated way in science. But if we want to go further and think about, really like automating the scientific method, then we're going to need to be able to generate hypotheses and design future experiments. And I think that this step with hybrid approaches is kind of a step in that direction. So I'll end with that. Thank you.
That was a brilliant start. Thank you so much, Kyle. A wonderful overview, I think, of many of the big issues that are facing us in this domain. And I can already see that we're starting to get the questions coming in. So do put your questions as you see the speakers so that we definitely remember to come back to them. But we're going to move now to Emily Sharkborough. Emily is a mathematician, climate scientist, and director of Cambridge Zero. She's also my colleague in the Department of Computer Science and Technology, where she's a reader in environmental data science. She's a fellow of Darwin College, the Cambridge Institute of Sustainability Leadership, and the British Antarctic Survey. Emily currently leads the UKRI Centre for Doctoral Training on the application of AI to the study of environmental risks. Over to you, Emily.
Thank you, Neil. Let me just, since everyone else was doing some slides, I thought I'd do some slides as well. So here we go. Oops. Let me just share that. So what I'm going to talk about, as you'll have gathered from the introduction, my area of application of my interest is around environmental science. And as Neil mentioned there, we in Cambridge have a Centre for Doctoral Training in the application of AI to the study of environmental risks. So I thought what I'd do is just give you a bit of an overview of where I see the opportunities, specifically in the environmental science side, for developing AI approaches. And for the most part, this is machine learning approaches. So specifically, I mean, within climate environmental science, my personal interests are predominantly around climate science. And so just to give you just a sense of some of the questions within climate science, there's a real increasing need for, if you like, actionable information around climate-related risks. So understanding what the climate-related risks are to society, perhaps in terms of the impacts on health, for example, or how to build resilience to future climate extremes that we might be experiencing in the future, or how to understand the risks of climate change inducing some major shocks to global systems, for example. And to help characterize those risks, there's increasingly vast quantities of data. Data coming from Earth observation from satellites, data coming from ever-increasing networks of sensors spread out on the ground, but also there's an example here of ocean floats that are continually monitoring the ocean, both at the surface, but importantly down at depth as well. computer simulations themselves, which are vastly increasing in the amount of data that we have available from physics-based models of the climate system, and so forth. And so, the question is, can machine learning, AI methods help us make sense of these vast data sets and therefore provide more accurate information on those climate-related risks? And as I say, this is one example of a much broader set of questions within the broader area of environmental science, which also includes many of the same sorts of questions associated with our understanding of the threats to biodiversity and conservation related issues, or the risks of arising from other environmental natural hazards, earthquakes or volcanic eruptions, for example, and the impacts of those on society. Just to provide a little bit more of a sense of some of the things that we're actually doing. Here's just 4 examples within the climate area of the sorts of ways in which we're currently using AI approaches to look at different aspects of the climate system and our ability to try and forecast changes in those different aspects. Looking at using AI-based modeling approaches to better forecast sea ice, which is something that is challenging to forecast because it involves lots of small scale processes and lots of different aspects of physics. And so it's just one of those aspects of the climate system that is fundamentally challenging. Can we use data-driven approaches to augment those physics-based approaches that have been traditional in the climate area? Looking at producing forecasts of future heat wave risk. Can we not only, again, use the physics-based models that we still have? This is not about throwing out the physics-based understanding that we have, but making sure that we are maximizing the value that we have from our understanding of past climate, the recent and distant past climate, by utilizing all the past observations of the climate that we have, looking at whether we can better predict future changes in the oceans, again using that combination of physics-based and data-driven approaches, very much looking at these hybrid models again that was mentioned in the previous presentation, similarly looking at improving flood forecasts. So that's just a set of the different types of things that we're looking in that one area of looking at climate and looking at how we could improve future projections. Overall, across this space of environmental science, I would argue that there are 3 key areas where I think that AI, machine learning methods can really provide significant opportunities. And those are, first of all, in the area of monitoring and predicting changes. Secondly, in the area of better understanding the environmental system. And then thirdly, in the area of helping to define some of the solutions to those environmental challenges that we face. So I wanted just to give you a little bit of a sense that under each of those headings where I think the opportunities might be. So let's go for the monitoring and predicting first of all. So I've already described in the climate area, and this is just as much true in the other areas of environmental science as well, that we really have vast data sets that we can deploy to better understand the changes that are occurring. And where some of the opportunities I think arise are that there are real challenges in terms of how to synthesize those data sets. Often those data sets might have different levels of uncertainty. Maybe the same key variable is being measured in multiple different ways, and we need to find ways of trying to synthesize those different types of data sets, and maybe an opportunity for drawing in non-traditional sources of data. So I gave an example at the start of looking at the health impacts associated with climate change. So are there data sets that we wouldn't normally have accessed from social media, for example, trying to understand the linkages between climate extremes and the health impacts associated with them. On the prediction side of things, I mentioned a whole set of ways in which we're looking at using AI to implement within our forecasts of different aspects of the climate system. One area associated with that is looking at how we can use machine learning methods within the parameterizations that are used in our physics-based models. Another area is looking to see whether we can entirely replace our traditional physics-based approaches with data-driven models, so exploring entirely new modeling approaches. And then a final key area that I think is important to highlight is whether or not, by adopting AI approaches, we can better utilize new computing infrastructure. If I just say a few comments around understanding, the key thing here, I think, is that environmental systems are systems. And what we want to be doing is looking at different ways of analyzing those systems. And so can we adopt AI approaches to get a better understanding of the structure of those systems, adopting things like causal inference to understand how one component of that system influences another component of the system, clustering analysis, and so forth. There's many different approaches that we could use to really get a better understanding of the key systems that are at play within these environmental problems. And then finally, turning to solutions, I frame this around some of the key challenges associated with responding to climate change. But again, I could have equally put down a set of lists around other environmental problems as well. But just to give you, these are the sort of major sectors of our economy that all need to be brought down to net zero emissions if we are to limit future climate change. And just to give you a sense of where the opportunities for AI approaches to be used in each of these. In the energy sector, there's a lot of work starting to look in many different aspects of energy systems, developing digital twins. Clearly, that's one way of optimizing the efficiency of energy systems. In the built environment, again, opportunities for that are already quite advanced in terms of introducing smart technologies throughout the built environment to reduce emissions. In the transport sector, similarly, maximizing the operation, looking at transport more from a mobility perspective than as discrete transport systems. On agriculture, there's a lot of work looking at how to introduce remote sensing combined with machine learning techniques to optimize our use of fertilizers or optimize the way in which we are where we're growing crops and according to the local climatic conditions. In terms of waste, a key aspect of reducing waste is to help support circular economies. And so how can we track things through supply chains more efficiently in order to support those technologies? Across industry more generally, can AI approaches be used to identify new greener chemical processes or new materials that can be used in different different parts of industry to reduce our emissions? Can we actually also look at how we can undertake AI-based computing calculations in ways that are less energy intensive? And then finally, approaches, again, potentially using either on the technology side, using AI-based approaches to identify new opportunities for actually removing greenhouse gases through engineering-based solutions, or looking at going back to the monitoring and things that I started with. Can we be using those approaches to monitor natural-based approaches to greenhouse gas removal and whether or not they are being, they're being as efficient as has been claimed? So there's a whole set of different ways in which AI approaches can be used on the solution space. So there, I hope that's given you a bit of a sense where I think there's enormous opportunities for developing this.
Brilliant. Thank you so much, Emily. That was a fantastic overview of the challenges and potential opportunities for artificial intelligence in climate science and, of course, weather. So next we have Yolanda Gill. Yolanda is professor in computer science at the University of Southern California. She is also Senior Director for Strategic AI and Data Science Initiatives at USC's Information Sciences Institute. And she's a former president, I think just recently finished her term, of the American Association for Artificial Intelligence. Her work focuses on the creation of intelligent interfaces for knowledge capture. Yolanda, over to you.
Thank you very much. I'm glad to go last because I am not a scientist. I am a humble AI researcher. And it really inspires me to hear about all these challenges and all these important problems in science that AI can help with. So as an AI researcher, I'll show you some thoughts about where AI is being underutilized in science. And I think it's very important that we push in these directions. So the emphasis that I want to make is that AI can really help in interdisciplinary scientific discovery. And sometimes I call this interplanetary scientific discovery. Why do I say that? It seems to me that often when we deal with big problems, when we study complex phenomena in science, different scientists collaborate and they seem to come from different planets. So one of my profound shocks was when we had a project to understand the age of water in an ecosystem. So we had hydrologists looking at the rivers going into lakes where the water was retained, and then the water keeps going into the out rivers. And to my surprise, hydrologists and limnologists that study lakes never talk together because lakes are considered to be small oceans. So they hang out with oceanographers a lot more than they hang out with people that study rivers. And so the chasm between their understanding of the problem, their models, their vocabulary was tremendous. And so sometimes I see that the scientists come from different planets and they're trying to come together and they speak completely different languages. Their models are completely different, their techniques, their approaches. And so it's really hard to address these larger problems. So you see that in environmental sciences, you see that in life sciences and biomedicine. So I think bridging across disciplines is a big role that AI can play. And if you see the trajectory of scientific collaborations, they're becoming more commonplace and more complex as well. So in the old days, a scientist would go in their corner, in their basement or their attic, as it may be, and spend years writing a book. Then we saw a period of co-authorships. These are co-authorship networks that I'm showing at the bottom. We saw periods of small co-authorships, then groups of scientists doing larger projects. This is a picture of the Human Genome Project in the early days. And so the collaborations were much larger. The one on the right is from the Atlas collaboration. I think Kyle is probably somewhere in there, standing in that big crowd. And they take years, and these are kind of hero science accomplishments, and I think that their accomplishment has been well recognized. And so what you see is the complexity of managing all of these interactions that need to occur. So I'm very interested in supporting this. And to give you a sense of the importance of these complex processes that we use to collaborate across scientists, I want to use the example of freestyle chess, where this is a style of chess that Garry Kasparov promoted after he was defeated by an AI system. For the first time in his life, he was defeated. And this game is about creating a team instead of a player. And the team is any combination of computers and humans of any capability. And what they found in playing these games is that the teams that had a superior process played better than the teams that had superior players. And so it's very curious that understanding your weaknesses, your strengths, and the areas where each individual and each computer system, each algorithm can help more, can lead to better performance. And I think we see this in many areas and many aspects of life. So AI has been studying scientific discovery since Inception. I think Herb Simon, who was one of the forefathers of the field, started looking at scientific discovery in the 50s and looking at how people thought about the data and made hypotheses and so on and so forth. And I have pictures on the left of Feigenbaum and Buchanan with Joshua Lederberg. Now that we're all watching helicopters in Mars, they were envisioning, Lederberg was envisioning AI living in Mars and looking at mass spec data and making hypotheses about the molecules and so on its own autonomously. So from the early days, there's been a lot of work to understand how scientists think, how science is done, and all the processes that are involved. One of the things that we've learned is that humans have a lot of limitations. So leaving science to humans alone to reason, to decide, to form hypotheses may not be our best bet for the future. So this slide may be controversial, but let me show you some examples of what I mean. First, humans are not very systematic. So I show at the top right a graph that shows work from Sean Peters comparing what an automated text extraction system got out of many papers about the fossil record compared to the fossil record that was extracted by hand over 10 years by Sepkoski and colleagues. And so the automated extraction was actually more accurate. To my surprise, I have to say, because I thought that the text extraction tools would miss out a lot of things that the humans would catch. And so it's really interesting that even though we trust humans to really read the papers, to really understand the papers, to really catch everything, there can be significant areas where we're not covering and we're not finding what's in front of us. Another example is errors that are made in the research. So this is an example from two Harvard economists that published a paper that a grad student at UMass Amherst could not reproduce, and after looking at the data found there were some errors in the paper, not in the results, but in the data analysis. So errors are not uncommon, and that's why it's very important to make science reproducible and to expose as much as possible of the work that we do. Sometimes they're very unintentional. We also have biases. So I show an example on the bottom right of an AI system that was able to look at paleoclimate data and create hypotheses from the data at hand. And what they found is that comparing the AI system's hypotheses to the hypotheses that the scientists had published in the papers, the AI system came up with more plausible hypotheses than the humans. And this is also not uncommon. And when the authors were asked, they said, well, we just like these hypotheses better. They just seem better to us. They seem more promising and they seem more likely, but they couldn't quite pin down why. So we may be biased in some ways. And then, we do poor reporting. We omit a lot of important details and things that are important for others to understand about our work. And I think there's a lot of published literature about this. So humans have some limitations. So we've been occupied looking at how to automate processes. So what you see in the middle of the slide is a picture of a workflow that captures the main steps that are followed in a scientific method. And then at the bottom, how AI is used to elaborate and add more steps and think carefully about all the constraints to come up with a sound, valid process to run the data analysis on. We've also been looking at the cycle that, similar to what Kyle was showing in his slides, this cycle of how do I formulate a hypothesis, how do I gather the right data, how do I analyze and synthesize results, and how do I reflect on the findings that I find, and formalizing what is a line of inquiry, how do I query data sets that may already exist, and how do I apply apply the right methods. We've automated this process for some aspects of multi-omics, data analysis, and also for neuroscience data. I think that this is a very necessary area for AI to do more in. And so what we find is that this is an example of a competition where people submit solutions, that people explore particular areas of the possible solution space, while we are able to do a much more systematic generation, rank the solutions, and really pop to the top the most promising ones that often corresponds to the top submissions to the challenges. We're also looking at interdisciplinary integration across hydrology, climate, agriculture, economics, to really understand how to affect a system and come up with interesting interventions that could really change things. So we look a lot at food security, and it really requires integrating knowledge across all these sciences. How do scientists do this? It takes them months or years to really do this. So we're trying to use AI to automate this. Ultimately, I think that AI systems could very well take on maybe the simpler tasks in science and write papers that have interesting contributions. So maybe a human is the first one that, you know, she might figure out how to calculate the atomic weight of an element and discover this new exciting method to do this. But then, you know, AI systems could catch on to this method and maybe discover the atomic weight of all the other elements. And I think humans have done this over the years, and many people got PhD degrees out of doing something that's very repetitive. And I see a lot of science being very repetitive. So I imagine AI systems cranking papers about very common things in science, you know, analyzing the genetics for this or for that or for the other kind of situation. And I think what they are missing is good principles for partnering with scientists so that we can really create collaborative processes for science. But I do see AI systems generating a pretty large part of papers of the future, and I think it will make everybody a lot more efficient for many reasons. So I think the next 2 decades will be really important for us to create AI systems that can really help with scientific discoveries. And I won't go into all the details of this, but I will tell you that I have a good colleague, Hiroaki Kitano, who has promoted the challenge of will AI systems win the Nobel Prize? And many think that by 2050 this will be possible. So I'll leave you with that thought.
That was really wonderful. Thank you, Yolanda, and thank you to all the speakers. We've had lots of questions coming in. If you haven't had a chance to look at the Q&A and you're in the audience, do please take a look and rank the questions or place in questions of your own. I really, really enjoyed that. So I'm going to just, of course, take the chair's privilege and ask the long first rambling question that really is just my excuse to hold forth on my own ideas. No, not really. But the what I was really taking out of the talks, I thought, Kyle, you had that wonderful view of the simulations at different scales, going all the way from, I think one of the things you introduced me to, the early universe and what its form was, going all the way down to sort of the small scale of the collider behind you. And it was making me think also with Emily, when you were talking, this one, you were talking about climate simulations, and I was thinking about the extent to which you start having to integrate across those scales. In particular, when I think you mentioned digital twins, and people are selling this promise on a digital twin of the Earth. And will we then be able to introduce, because of course it's human social impact and interventions affect humans, so there's sort of, can you actually start simulating across the scale from the human to the sort of down to the Navier-Stokes? I mean, or is this a sort of crazy idea to put all of this in the same simulation? And then that was just making me think that a lot of this feels like it's about interfaces, because that's interfaces between different sub-simulations, the simulation of the human, the simulation of these different physical processes at different scales. And then what Yolanda was saying, which I thought was so important, which is about the integration with the human and the understanding and the AI as co-author. And actually, how do you gain the strengths of both? But it left me with an impression that is maybe the main role of AI just to get these different subgroups talking to each other in the same language so that they can explain it to us. Maybe I'll open with that for Emily, or any of your thoughts on the other speakers, Emily.
Yeah, okay. So maybe I'll start with digital twin of the earth, or the whole system. Is that ever going to be possible, right? So so before we all get carried away, one of the things that's always going to be a challenge if you are fundamentally doing a data-driven model is pushing that model outside of the world in which it's been trained, right? And climate change is precisely doing that. And so part of the reason why I was emphasizing so much these hybrid approaches is because actually the one thing that physics is useful for in this context is providing us with a framework for helping to deal with the, if you like, the non-stationarity of the climate problem, right? That we, and so I think that are we going to have ever a purely data-driven model of the whole of the data-driven and digital twin that is going to be able to provide predictive power throughout all of the different things that we might be interested in? I mean, I can't see how we could possibly really, but is there a really valuable role? And I think this came out in quite a few, both presentations, for looking at ways of connecting together different modeling systems, that are different components of that have perhaps not normally really been able to interface together. And I think there might be real opportunities for data-driven approaches, AI approaches, allowing that to happen. And just one example where I've been interested in exploring whether or not that might be possible is linking together all of our understanding from a more physical biological perspective of some of these problems with the economic modeling. And the structure of economic models is utterly different. And those are all based around optimization. The physics biological models are all based around predicted models based on our hypothesis or understanding of the laws of those systems. It's quite difficult for those two traditional models to speak to each other. But if they can speak to each other via the medium of a data-driven model that connects the two together, then you can start to see how you can start to get these systems. So I think there's interesting ways of connecting up from a systems perspective many of the different components, but whether or not we're ever going to have actually a digital twin of the whole. I mean, we have a perfect digital twin of the whole system, which is the system, but it still doesn't allow us to predict into the future.
Yeah, I thought you were making me think of some work in the pandemic where we were working with epidemiologists and economists who were very keen to try and link their models, but it is so hard because of the different levels of granularity of which these models are working. And I think also the nature of the risks. The economic risks are often near-term and very tangible, but as you say, the long-term risks are very severe, but much harder to talk about and make the comparison. But some of what you said also related to that wonderful quote that Kyle had from Peter Norvig with that extraordinary shirt. It was sort of a hypnotic shirt almost, which said to us that all you need is the data and that it's the end of the model. And we got a question from Andrei Palais, who's to Kyle, which is there another point behind Norvig's claim? Because all simulators are models themselves. And they're not entirely correct representations of theory. And sometimes we don't even know how exactly different they are from theory. And so what do you think the best approach is to exploring this gap between simulators and reality? Use data to augment, correct, or replace simulators? So starting with that sort of, was Peter serious, or is he just being quoted for effect?
Yeah, well, I mean, I'd be curious about what other people think, but I mean, it's certainly true that, like a computational physicist that's say studying fluids and maybe even for climate, you know, there are equations that are written down like Navier-Stokes or something, and then you put them on a computer, and with limited computational power, you can only do so much. So there's a gap there. I don't think that's what he's talking about. I think that he you know, he's not worried about these kind of fine details. I think it's more like, you know, it's more about the actual assumptions. The whole model itself is maybe, you know, they tend to be wrong, you know, like, and so there's this idea that statisticians have that don't take your model too seriously. I mean, I think particle physics is one of the weird places where maybe we actually do take the model pretty seriously. But, you know, other than that, you know, there's always like layers of approximations. And I think, you know, the way I read that quote is very much that those approximations are there and they're significant, and you can maybe just get rid of them if you have a lot of data and just move to something totally data driven. And I think that, you know, data driven is a weird word because of course it's a spectrum, right? So when you're coming from something that's a typical way that scientists have done something with, a, you know, like a equation that you can write down on a piece of paper, and you start moving to something that integrates more data, it starts to seem more data driven, that's for sure. But there are usually still layers and layers of assumptions that are going on in there. And so the way I read Peter's quote was much more like, you frame the problem as a predictive problem, throw a bunch of data at it, and just forget about like traditional scientific theory. I don't know if others disagree, but that was the way that I take his quote, not about small differences and you know, and the kind of the theory and like the computational manifestation of that theory. I don't know.
See, perhaps I think you were involved in this Twitter conversation with Austin Lamacraft recently on the new term in the Hamiltonian. This is the new force, and what that means. And I don't know if you remember the conversation I'm talking about. Perhaps you could elucidate that, because I think that's a very interesting example. Where's all that coming from? How does that fit in? Perhaps you could give a bit of the background.
Yeah, I mean, I think the to me, the point in terms of going to the second half of that question about like, how do you move beyond it? I think that a lot of the, you know, the interesting part about the data-driven AI part is that the traditional approaches that we had would have, you know, scientists want to have Occam's razor and they want to be kind of as parsimonious as possible. So they have a simulator and they only put as many bells and whistles in there as they kind of need to. And then already you quickly get to a simulator that is kind of too complicated to turn around and do inference with. And so once you have a simulator that's too complicated to look at some data and try to infer the parameters, then what's the point of adding more complexity to it, right? And so I think that there's been a natural, you know, leveling off of adding more complexity to the simulators. And so then you see, you know, the deficiencies in those models from what you actually see in the real world. But with AI, what we're finding is that, okay, we can add a lot more complexity to the model. It doesn't have to be parameterized the way that scientists would have typically parameterized it, and we have much better algorithms for trying to fit it to the data. And so we can effectively start to describe, you know, so like all these residuals where there's all the ugly crap that you don't really understand what's going on, you don't necessarily care about, that stuff is great for like neural networks and things, right? Just parameterize that as so, but then you want to usually graph that on top of some kernel of truth that's much more interpretable, like, you know, fluid flow and, you know, basic, you know, heat convection through the Earth system or something like that, right? So even in particle physics, like the microscopic interactions I can write down on a piece of paper, but like interaction with this thing behind me is very complicated, right? And I'm happy to use machine learning to describe that thing. But once you're done with that, I think this is the important point, is once you do whatever that particular scientific task is, what do you do next, right? And this is where interpretability is important. Like if I look at the data and I throw away my theories and I have some model that fits the LHC data and it finds something, like what do I do next? Like what experiment am I supposed to do? I can't look in the weights and biases of my neural network and figure out what to do, right? So unless my model is structured in some way that maps on to the concepts in my brain, and this is very much related to Yolanda's point, you know, and also the point about building an Earth scale system and interfaces, right? You need an interface not only for bridging between different scales of the problem, but also communicating between humans and multiple different humans, right? And if the way that the knowledge is represented in your AI is completely scrambled compared to the way that we think about things, you don't know what to do next, you know? And so that's a specific notion of interpretability that I think we have to maintain. And I agree, it has a lot to do with, you know, grouping the system into subsystems and interfaces and and like essentially an ontology of things. You know, there might be machine learning components, but you still need to break the thing down into subsystems.
I think that was a really insightful answer, and it sort of triggers a thought in my mind, which I think becomes as more of a question for Yolanda. It's because it's a sort of, maybe it's more of a question for us on the AI side. One thing I kind of like about AI and what it claims to do, and as I think Kyle was hinting at there, this starts asking questions about what do we mean by human understanding, or our ability to say that we understand that bit of physics. Because if we're saying, well, an AI can predict it, does that mean that we can understand it or not? So how does that interface come in? Because there's this sort of point at which, as you sort of said, there's some things that the AI can do that we can't do, that just with the quantity of data it can look at, that it can distill and make predictions and so on and so forth. But how does that then interact with the nature of what our understanding of the underlying science is? Or does it not even matter?
So, you know, it's maybe a great coincidence that AI is about understanding intelligence, right? Because I think more than interpretability, what we want is knowledge integration. We want to understand how we take some understanding, some result, and integrate it with our existing body of knowledge. And so knowledge integration is very challenging in itself. You have to have some place where you have a body of knowledge, some knowledge base, and you have some new piece. You have to understand if it's a monotonic addition that just extends your current belief, or if it actually disrupts what you believe in, and you need to retract some pieces, and what holes does it leave? And that's how you get to the questions that Kyle is saying you want to ask next, right? And so that whole process of knowledge integration is something that we've studied in AI, and I think we need to incorporate it more with these ability to analyze data and build simulators and make some predictions. How do we turn that into some knowledge that we can integrate with our current beliefs? So I think that that ability to integrate knowledge together and revise knowledge is very important in science. And just looking at data is not going to get us there. We need to be able to see you know, bodies of knowledge grow and evolve and be wrong and move forward. How do we support that with AI systems?
Yeah, I think that really excites me as well. This sort of like, I'm not always that keen on the fact that suddenly it seems that I research intelligence, but I really love that notion of it, that what it means for us to understand, and as we try and automate that process, trying to take it down into, because I think we've talked about some of the sort of bigger issues around the problem. And I want to get a bit more practical with the question from Monchil here, perhaps to Emily, which is what sort of kind of AI models are nowadays commonly used in these cases, and what kind of guarantees and interpretability do these models currently give us, and how do we decide whether to extend trust to these models? Emily, I wonder if you could have a go at that, sort of like specifically what models are we using, and I guess how do we get interpretability, and how do we trust what they're outputting?
Yeah, actually, I would also, some of that I'd like to bring in Yolanda's answer to some of the last question as well. So maybe I'll start there, which is the knowledge integration piece, because I do think that that's really important. So if let me take this really specific example just to kind of give the sense of it. So if I'm wanting to better predict something around mountain weather or something like that, which is through our traditional, the traditional weather forecasting approaches, that's all based on, well, Navier-Stokes or Newton's second law or something. That's how we've developed our weather forecasting models, and it's the heart of all our weather forecasting models, with essentially Newton's second law solved on a grid, and everything below the grid scale is parameterized, as was mentioned a moment ago. So what sort of approaches are being used to introduce data-driven approaches within that framework, those parameterizations, which are actually largely data driven in the first place. They're empirical based parameterizations. You can look to replace those with machine learning methodologies, for example, or you can look to replace the whole of the physics-based approach with a time-stepped iterative process that takes the conditions at one time step and then uses a machine learning approach to iterate to the next time step, and you replace the whole of the model that way. But what you're not doing, so in the it's always been the case that I think a lot of people in the environmental modeling community would understand that traditional local knowledge is always also critically important. There's no coincidence that the Indian Met Service does a much better job of predicting tomorrow's weather forecast for India, or traditionally has done, than somebody sitting in elsewhere in the world. Partly that's because typically those models will have much higher resolution over that local region, but there's also because there's been local expertise that's been inputted, and that's if you take the problems out, then that local knowledge is always critically important. So if we can find a way of appropriately synthesizing and integrating that sort of human knowledge with artificial intelligence, then I think that starts to get really exciting, and working out the frameworks within which we can do that.
Is the onus fall, you're making me think, and maybe this is a question that's going to shift, but does the onus fall on us to be doing that, us to assimilate the machine, or the machine to simulate us?
I don't know, but you know what, I think it also relates, and I think there's a really, this hasn't been done in a systemized, although there's a widespread recognition that local traditional knowledge is really important, there's not a systemized framework really for properly integrating that. And maybe this is, maybe another area on which AI can really genuinely be powerful in advancing the, scientific process, is by providing a more coherent framework for systematizing that integration of local traditional knowledge.
I'm also
but obviously that then opens up a whole plethora of cultural, ethical questions in itself, which is, I guess, not the way in which we've traditionally been thinking about the way in which ethics intersects with AI, but I think is also important.
Perhaps an easier question, but also a challenge, which was just occurring to me as you were saying that. I mean, there's still a problem even just with integrating different simulations.
Oh yeah, no, exactly, of course, yeah.
And one of the slightly irritating things I think about a problem like that is, I think it's no one's specialism, is it? It's sort of like, well, it is people's specialism, but it doesn't get you the Nature papers, it isn't the cool advances in, but it's the really difficult work to actually make the whole thing stitch together. Is there a parallel between that type of work and actually integrating human opinion? Are we just another node in that compute cluster, or is it much, much more complicated?
Yeah, I don't know. Well, but I question whether or not, your hypothesis that it doesn't get you the Nature papers, actually the intersection of different fields is often precisely where you get the Nature papers. So.
Yeah, well, and it relates back to Yolanda's point about the scale of collaborations and consortia that are needed. And I had a question that maybe we'll come back to later if there's time, about what does that mean for credit in the scientific age, and people's desire in academia is so focused on credit, but we'll come back to that perhaps a bit later, because I'd like to make sure we get through the questions in the chat. And I really like this one from Mark Farragut, which is for Kyle, but I think also we'd like you to have opinion from Yolanda and Emily on this. Do you see causal ML as being widespread in 10 years? There is some open source effort in this area, for example, Uber's causal ML library, but hybrid approaches like this still seem to be in the very early stages. Kyle, let's go to you on that, and then I think we'll come to Yolanda.
I'm curious to hear what everyone thinks here. I mean, I would guess so. I think that sometimes what happens is that there are things that they might not be branded that way, but even if you look at, for instance, what's happening with like graph neural networks, a very quite popular thing that's going on, and we use them occasionally in physics. What's interesting there is that we often take for granted that there's an architecture, but then we go to, say, apply it to a problem where you have a bunch of gravitationally interacting bodies that are moving around, and you want to predict the system, it's just kind of obvious that the nodes in the graph should be your planets or whatever, and the edges are basically like something like forces, and when you attach that kind of structure, that architecture to the system, that causality, a lot of these causal ideas are like happening right there, and you might not even recognize that they're happening, right? There's nothing stopping you from mixing it all up in some confusing way. And if you don't have the kind of, if there's a big mismatch, those kinds of models aren't going to work well. But when they line up nicely, they work incredibly well, right? And so there's a ton of research that's going on about kind of, often under the name inductive bias, about basically just, and a lot of times that inductive bias, I feel like, is a soft form of the of causal inference. It's not really like specifically cast in the typical way, but you're starting to see a mirror between how the architectures of these things reflect the mechanism that's going on. But I think what's interesting, and you see research that goes on, and for instance, how robust are these, for instance, to like domain shift, or I mean, that's a notion of causality in some sense. You're thinking about, if I perturb the system in a certain way, how is it going to respond? Or all the work about like zero shot generalization, or just all of these kinds of things. They're basically all pointing to causality in one way or another. So I think increasingly, people are exploring those connections, and it might become more explicit. But I feel like there's a ton of directions and current research that are moving in that more causal direction.
Yeah, so I think of course there will be widespread work on causality in 10 years, particularly in all of these science applications of AI. So we know already that from early days that machine learning systems that just propose something but cannot really attach the functions or models to some causal understanding that extends what we already know, they're kind of not very helpful. So I do think that the causality will become more and more prevalent. What you read more in papers and in the press may be low-hanging fruit, but there is a significant amount of work on causality, particularly for problems that have a temporal component, where causality is perhaps a little more accessible for automation and machine learning. I think there's an aspect of causality that's very important. So one is the causality in the sense of being able to propose a causal model based on the data that you have in front of you. There's another aspect, which is to validate that causal model, or to debug it, or to figure out if it makes a lot of sense or not. So you see children sometimes creating causal models like, somebody came and they took the cookie, and that's why the cookie disappeared, right? So that's a great causal model, just that you have to validate it, and you have to understand the plausibility of it, and you have to refine that causality and consider other possible hypotheses. So it is in that aspect that I think we haven't done enough research in, that will be more and more important in the coming years.
I totally agree. And I think there's something, and come to Emily on this as well, but with a sort of thought that there's something particularly contextual about the way humans tend to use causality, because of course the example Kyle gave, well, we accept that planets are things and they can be represented by a center of mass and everything else. But the ability of the human to sort of abstract a class and start talking about causal relationships between abstract classes that humans have created on the fly, without starting with Navier-Stokes or some low-level physical simulation, and yet use that predictively, fascinates me. And I saw some sort of, particularly because we used to do this sort of stuff in the Amazon supply chain, and the causal, there isn't a physical underpinnings, there is, but it's also abstracted. And the answers people are wanting when they ask about what went wrong in the supply chain are so contextual. And that really struck me as being quite related to when Emily was sort of laying out the three areas. And I think you mentioned causal inference in your central area, which I think was the systems area, Emily, which fascinated me because it's a sort of understanding at a at a meta level, it's like, yeah, well, we've got a load of physics in this model, so we kind of understand the microscopic causal relations, but this is more of a macroscopic causal relation. I just wanted to explore where the tools are for that, Emily. I mean, or if I misunderstood, you can say, well, that's totally wrong and that's not the issue.
No. So I mean, the way that I very much had the causal inference in that middle bucket that I had around understanding, and I think that applies both at the level. So we have physics-based models of the climate system, as I've been describing, but those models, although we know the rules, the laws of physics that have gone into them, but even if we just take a model only of the atmosphere, for example, there's still, as a whole, too complicated. There's too many things going on that are connecting the different scales. I mean, the scale line that we've seen a number of times that Carl put up, there's too many different relationships that can happen across those different scales, up and down, that mean that actually understanding if you hit the system here, what's going to happen over here is not at all straightforward. So within a single model of a single system of the world, then actually those questions of causal inference and understanding the system in terms of causal inference are incredibly important. So that's one whole class of challenges where I think there's opportunities for causal ML to really improve our fundamental understanding of systems. I think there's also opportunities in much more complex systems. So for example, at the moment, I'm interested in looking at entire landscapes and how we can intervene in landscapes to put in place some measures that would have benefits both for climate and biodiversity, and also for the social context of the people that are living in those systems. So could we also be looking at causal inference in that context? If we intervene in that much more complex system, what are the outcomes associated with that? I mean, that's an infinitely more challenging problem, but also potentially interesting.
The example, I think, relates to what you were saying around the atmosphere. Tell me if it's a poor one, but I got it from Neil Robinson, who works, or what used to work at the Met Office, where he was telling me that one of the things he had to write for the simulator was a hurricane detector, because of course hurricanes aren't explicitly represented in the simulation anywhere, but it's kind of a pretty major thing that you sort of want to know about. And I suppose the sort of thing that you might be interested in, and one could argue, well, it's just a human abstraction of the underlying physics, pretty obvious one, I suppose. But then you've got El Nino and things like this phenomena that we also describe. And so with the sort of thing you're talking about, I want to be able to describe whether El Nino caused this hurricane or caused an increased number of hurricanes. Is that sort of abstraction level, is that an accurate summary, Emma?
Yeah, or I mean, another example where I've had students who've been looking at it is you might have heard sometimes people talk about, oh, the polar vortex has been doing something and that's affected our weather, in the United States or in the UK, and the polar vortex is something that sits high up in the atmosphere, in the stratosphere, and so understanding how changes that are happening in the polar regions high up in the atmosphere have then a knock-on effect on weather in North America or in Northern Europe. There's a set of causal relationships associated with that are very complex in terms, and they may or not be how they're represented within our models, our numerical models, as opposed to how they really emerge in the real world. They may or may not be the key kind of steps in terms of the physical processes may or may not be accurately reproduced in our current models compared to the real world. So causal inference within our model world and causal inference in the real world may not be the same. That's also interesting to explore. So there's all sorts of questions that you can very quickly get into that are really fundamental science questions. And that's where this combination of the artificial intelligence and the human intelligence connecting together starts to be really interesting.
I love what you're saying, Emily, and this idea of the abstractions and the understanding of these causal relations and the causal inference. I think there's an area in AI that's not very well known. It's called qualitative reasoning. And I think the idea of taking, numerically grounded models and theories and being able to abstract enough that you can start to ask questions and understand qualitatively what is happening. I can't imagine in the climate domain that the techniques that we've developed so far are pretty humble. They have to do with engineered devices that are pretty simple, and physics processes that are pretty mundane. But at your scale, I just see a lot of research ahead to help us transition from the quantitative to the qualitative realm in a more subtle way. And maybe that's a path forward in terms of exploiting machine learning and data and connecting to the human understanding of the mechanisms underlying.
Yeah, can I chime in? I think that this part of the discussion is really fascinating. I mean, I think for a few things. One is that I'm fascinated by the human's ability to also, we have models at all these different scales, and we have some understanding about how they match up and connect to each other, and climate is very difficult, but there are other situations where it's a little bit more clear cut, like from atoms to molecules to cells to humans to, or something like that. You kind of know, you have a picture of what's going on at these different scales. And when you ask a certain question, we kind of immediately know which is the appropriate model to pull up, right? And then you can kind of, in your mind, you can reason with that, and you can, and so if you just worked at the macroscopic one, you'd be burning, epic amounts of compute time or something trying to, model a bunch of totally irrelevant stuff. And I think, that ability to not only have models at different scales and some understanding of how they're connected, but to be able to zoom in and out between them and navigate. When you think about how do you design the next experiment or what kind of intervention you might want to do, we're usually working in that, these very, kind of a coarse-grained picture of the world, and it's really fascinating how we're so good at being able to do that. Anyways,
I totally agree. I mean, it sort of maps onto experience I've had modeling Formula One races and modeling, say, the supply chain. Both those things are quite interesting because they're less like, this is the laws of physics that I'm going to include, and more like, I've got a variable representing polar vortex, and I've got a variable representing, so I've got variables representing cars. And one of so despite humans' ability to model this quite well themselves, their ability to understand the level of granularity of a particular model and not start adding too fine a detail in some parts. So when you don't have the model directly tied to the physics, I think it becomes very hard for people to understand what should they include in the model and what should they not include in the model. There was an incident with one team where they were insistent that we had to have an if statement around the driver who was in front, because there was a particular driver that was a development driver that was always going to let their car by. And so they wanted to make sure, well, no, that has to be included because we know that's true. But it's like trying to explain, but it is true, but it's not the level of granularity at which this model is operating. We've got a little probabilistic model for overtake there. And trying to explain that to people when the model isn't physics, it feels very hard. So although humans are good at it, I don't think they're very good at it when they're released from I don't know if that made sense. You're just triggering thoughts from my own experience there. But perhaps I'll go back to
Neil,
go ahead.
Sorry.
Go ahead, Yolanda.
I think you're hinting to something that's incredibly important, which is the translation of scientific results or scientific understanding to humanity, to everyone, so that we can change our behaviors or improve our behaviors, right? And I think this is an area that as scientists, we have a responsibility to do, because oftentimes, people are the hardest thing to influence and to maybe the easiest and the hardest thing to influence. But, to really translate your physics about, how the car is racing to the human team's informal, non-scientific understanding, which has incredible amounts of accuracy and expertise in it, right? But to affect that is really a profound, goal of science, right? To really help us improve our world. how do we do that? So that adds a whole another layer that it's not abstraction and it's not qualitative reasoning. It just goes beyond that in mapping maybe scientific understanding to common sense, to domain expertise. I think it's very important to do that mapping and translation.
I think we've particularly seen that with the pandemic, obviously, in the near term. And I guess Emily's presumably resonating heavily with Emily around climate. And maybe it relates to, I think, Anita Fowles' question, which is science too much in the public eye? But the way I'm partially interpreting that is almost everything we've discussed is messy. And there isn't a clear and definitive answer, particularly as we get around these interfaces of these things and how we interpret it and what we understand. And we know where things can go wrong. But somehow it feels like there's a perception amongst the public that science is clear and definitive. And maybe it is at some point. I'm not sure it ever is fully definitive, but the process of getting there is quite difficult. And maybe Anita's question is hinting at this issue that as the public sort of sees under the hood of what's going on under science, and you've got all these conflicting opinions, you can just select any one of them and say, well, that's all rubbish. How does that interact with this process, if at all? Perhaps go to Emily first on that, because it's been such an issue for climate science, right?
Yeah, and the thing is that ultimately, well, maybe it comes back a little bit to one of the things that I said about actionable information in the climate science world, and many other, pandemics, another example. Real decisions have to be made based on our best available evidence, and that means that this whole issue of uncertainty and making sure that uncertainty is appropriately represented in all our methodologies and then appropriately communicated is really important. And that uncertainty can come in, we've been talking about, any AI-based approach is going to be reliant on the quality of the data that's going into it in the first place. And so making sure, and we certainly don't have perfect data, many challenges as one could identify in terms of that, and then of the methodologies, and that comes into the interpretability of the methodologies as well, because that's sort of critical to the trust associated with the evidence base that's coming out of it. So there's multiple different ways in which the characterization of uncertainty, and the flip side of that, the trust in the methodologies is critically important to our ability to be able to take the information that's coming out of these systems and make actual real world decisions based on it.
Emily, do you feel that we all have to get better at communicating that publicly? Or is that just the responsibility of a few of us?
No, but actually,
can you do that for us? Or is it what I'm saying?
But I think it's actually also more fundamental than that, because additionally, there's, one of the things that we've often really struggled with in the climate community is there are multiple different types of uncertainty, and how to create a framework such that we can communicate all those different types of uncertainty at the same time. So there's the kind of classic Donald Rumsfeld's thing about the known unknowns and the,
we never knew when he first said it how deep and important that was going to be across the sciences.
But that is a real challenge, right?
It's a real challenge.
So I can, I can define the bounds on which I can provide information and, with, put all the caveats in. But in the real world, you've got to make a decision that that doesn't have all those caveats in it, that it somehow incorporates all the different types of information. So, I don't know exactly what's going to happen, what the risk of the Antarctic ice sheet collapsing and us having many meters of sea level rise. I know that it's a risk. So there's a set of uncertainty. There's another set of uncertainty where I can put on actual sort of quantified error bounds associated with it. And somehow we need a framework for integrating all of that. And again, it may be that actually there are opportunities in the AI space for in terms of that sort of synthesis of different multi-fidelity kind of approaches to actually help us in terms of some of these communication challenges when it comes to communicating around uncertainty.
So if I may, so I think about this topic a little bit differently, and I'll say that I hope that AI will make us all better people. I think people, the public, and myself included, we are not logic and consistent. We don't look at evidence, information, and data and all decide in the same way. So 2 decades ago, I had a project to capture rationale of decisions. And my final report was, it's hopeless. People don't make decisions rationally. They don't realize that it's the color that's making that digital camera more interesting, or the shape of it, rather than all these technical things that it's supporting. There's something else that they're not even seeing. So we are learning a lot about modeling the emotional state of people, modeling the affective state of people based on baseline biological measures. And you just find a tremendous influence on the mental and emotional state of people in their decisions and in the way of doing things. And I don't say we are scientists or we are very logical. I think we are also people. I caught myself last night discussing a particular topic, and I caught myself saying, you know, logically, I should agree with this. Somehow my gut is not happy with that agreement. So I'm going to stay quiet. And I stayed quiet. So I think that we are at a point where in science, the social sciences are so important. And I think they will tell us a lot about, you know, how the public understands, how the public reacts to facts and data, how we all react to that. I think it's not just a matter of us conveying the message better. I think there's also some understanding about how people work and calling people on their, you know, their inclinations and their decisions when they're not very rational. You know, this well-known study of judges that they give much harsher decisions right before lunch when their stomach is empty, right? So how can we get AI to make us better people and call us when we're being biased, when we're being, you know, not logical with our decisions? And we find this all the time, decades of research on water shortages in California, and we present all this science data to the farmers, and the farmers say, yeah, that's what we all should do. And then they go home and they do something different. What happens, right? Why do we behave in these ways? So people are perhaps the more challenging aspect of having science really influence decisions and result in interventions that will help us improve things.
No, I think that's really important. And it's like, you know, if you tell people there's a 10% chance of something really bad happening or a 90% chance of something really good happening, they interpret it completely differently, even though it's exactly the same information that's being conveyed. So there's all sorts of ways in which the framing of things and, you know, so many different aspects where that irrationality feeds into the decision-making process.
Brilliant. What I'm going to do now, I'm going to go to Kyle to see if he's got some input on that, but also then you can segue into Kyle's final thoughts, and that could include anything you wanted to bring up, we've not brought it up, or one of the questions you think that we should have touched, because unfortunately we've not got to everything. You've been far too interesting about the pre-existing questions, and then we'll cycle through everyone in the original order. So Kyle, thoughts on that, or
yeah.
final thoughts?
Yeah, no, I mean, I think I've certainly thought on similar veins. I think, so one observation that I'll say is that on the AI machine learning side, oftentimes things are cast like, you have a clear objective and you want to optimize it. And there's this hyper rational notion of like, to go do that. And anything that's somehow not optimal is then characterized as being irrational, which I think is an even more extreme notion. So for instance, when we build like this big experiment behind me, it's a multi-purpose experiment that does a lot of different things. And when I first started working with machine learning researchers, a lot of times you're like, tell me what your goal is. And it was also at the peak of like end-to-end learning. Like, you want to discover the Higgs boson, you have data coming in, I'm just going to optimize this entire pipeline. And like, just tell me what is it that your objective function? And I'm like, well, okay, well, and so at some point I kind of agreed with them, and I'm like, yeah, physicists really do a poor job of just saying like, what is our goal? And then we'd start to kind of clarify that. And then there'd be a solution. You're like, oh, but we can't do that because there's other concerns. And the machine learning and the researchers and statisticians would get really frustrated that we kept moving the goalpost. And then more and more I started to realize, well, partially it's because we're trying to do a lot of different things. There's not one clear objective, or there's a bunch of objectives and I have no idea how to weight them. So there's a sort of multi-objective heuristic thing. And you think about how hard that optimization problem is. And then you think about how humans, through whatever way it is that we do it, are kind of managing that. And part of it, I think, is also decoupling that we're necessarily optimizing everything. We have like we have this picture about roughly how it's working, and we make a lot of heuristic decisions under limited, resources. But so I think I think a lot of humans also are kind of coming from that direction. So maybe part of this communicating better with people is also to embrace the fact that not everyone thinks about the world that way, and that it's also not irrational necessarily to not hyper optimize everything. There are also scientists, a lot of times they want to be seen as very objective. And so they're sort of like, here's my data. I don't want to have it say anything more than what the data says. I don't want any, Bayesian priors in there beyond what I need to or something. But if you then need to make a decision under uncertainty, that's, when you frame things more in a decision theoretic sort of way, you start seeing that, where the rubber hits the road. So maybe there's something to be gained when you're starting to talk to like policy people or business people that are used to like, I need to make a decision, and there's some uncertainty, but they don't necessarily formalize it because they're working with heuristics and et cetera all the time. So maybe we can make some progress in sort of recognizing that. But I think that's partially on the AI machine learning side, is to not necessarily insist that everything is like optimize the objective function or you're a loser.
Great, I like that. Yolanda, sorry, it'd be Emily next.
Yeah, so I think this kind of rational, irrational framework is actually a nice way perhaps to describe the entire conversation we've had over the last hour, where, there's a start with the sort of the rational perspective of looking at, how AI can be brought in methodological ways to help interrogate problems. And we've ended up in a much more irrational space, if you like, of actually starting to, in a arguably much richer way, starting to interrogate these problems, and through a sort of inspired by the lens of looking at systems from an AI's perspective, but then interrogating in all sorts of other dimensions that we perhaps wouldn't have thought of from the more initial kind of rational methodological approach. And I think it shows how maybe in a generic sense, taking a fresh look at a whole set of problems through a completely different lens can lead to such rich discussions. But I think it also has highlighted there are all sorts of different, very varied avenues that AI research can take in terms of helping us to better understand the world in which we live.
I really like that too. Yolanda, final thoughts.
So I think this thought that I have about AI helping us become better people, right? I imagine, some AI eventually, accompanying us and being kind of a second conscience and telling us, that's interesting that you did that. I don't know why you're doing this, and kind of helping us understand our decisions better. So I think that will have a cumulative effect on humanity to be better people. Why did we get upset at somebody? Why did we show up late to something? Why did we skip some exercise routine that we were supposed to do that day, etc. So, and the same thing with science. Why did we express this, or why did we question this? And helping us. if not to believe the evidence in front of us, at least to be able to articulate better why we doubt it, or what else would we want to see that would be convincing or interesting to us. Unfortunately, we don't have a lot of time to wait for the research to catch up with these, giving me a second conscience. But because today we have people making decisions and having the ability to make interventions and spending millions on trying to improve situations and not succeeding. So I think we have a much more pressing responsibility. So we're doing a lot of work on trying to put scientific models and bridge them to decision makers. So before convincing the public, can we give decision makers a much more qualitative and quantitative set of options and helping them answer questions, helping them think about problems, taking their follow-up questions and turning them into something that our models can answer. That's a space that I think science and decision making need to come much closer together than they have so far.
Well, a great place to end. Science and decision making coming much closer together and becoming better people along the way. So there truly is a lot at the interface of AI and science. I'd like to thank, we've run out of time, unfortunately. I could have definitely gone on to all night with that. I really enjoyed all our speakers' contributions. I'd like to thank Kyle, Emily, and Yolanda again. And to any attendee who'd like to find out more about our work, our website is almost up. It's going to be up very soon. Keep following us on Twitter or follow me on Twitter, and we'll provide it when it's there. And you'll be able to sign up for a newsletter about future events. But if we could just sort of thank very much our speakers for what I found to be a fascinating discussion. And thank for all our attendees for their questions and for attending. Thank you.